Welcome to the latest video in our series on image diffusion filtering. In the last few videos we saw many different ways to solve the heat equation, like either in one dimension or in two dimensions, and either exactly with the Fourier transform or with approximate methods using implicit explicit methods or a mix between the two, like the Crank-Nicolson, the ADI for a 2D case. And then once we introduce these methods, you might ask yourself, why do we even study them? Since the FFT method is already pretty fast and it gives the exact solution. Well, the reason is that usually uh, we don't implement the linear heat equation. There are extra terms, there are extra nonlinear terms that are important for a more interesting filter, for a more interesting numerical simulation. If you are into science stuff, or if you want to study the evolution of a scientific phenomenon, usually the equation will be nonlinear, right? And what happens is that the Fourier transform does not have a generalization when you add these nonlinear terms, while with the approximate methods you can actually generalize them to include nonlinear evolution, and this is what we're going to see today. So we're going to start now with this slightly modified heat equation. So we see here, this will be 1D, alright? We're going to start simple, straight to the one-dimensional case, then we'll later go to two dimensions, and then we have the typical heat equation term, del U del T equals d del square U del x square, and now we added this, minus b modulus of del U del x squared. Right, so here it could like remove the modulus, because since this square is always positive anyway. But the idea is that these will represent in two dimensions, this will represent the gradient, the modulus of the gradient, right? And this is kind of a dumb example, because this nonlinearity does not change much with respect to the linear heat equation, but it is an interesting example for us to study because it's for two reasons. First is because this gradient square term appears in a lot of filters, because the gradient is some sort of edge detector, right? So if we go to Krita, so suppose you have an image. Oh, sorry, let us pick color black. So I have an image, right? And then at some point here, you will have an edge in this image. And if you, for example, if we do a cut here and we see, it could potentially be all black here, right? So also here could be black. So if we do this cut, you will see that in the graph along that blue cut, if we plot the brightness of it would be, well, suppose, I don't know, here outside is blackened, but it will be something like this. It will be a jump. And then this is if you plot the field U, while if you plot the gradient, it is the derivative of this, you would actually have something like this, right? This is the derivative with respect to x, if you want. And then, well, this could be the other side. You could have, in this case, we have black on the left and white on the right, but it could be reversed, and then in that case, this thing here would flip side, would be upside down, so that when you take the square, it is always positive, right? So this function, this gradient square, kind of detects edges, in the picture, and sometimes you want to have an effect like that. You control the diffusion close to an edge, right? And what actually happened, and then there's another reason that we study this guy, is because when we add this minus b term, this nonlinearity has a very easy effect to see, and then you can actually validate if your solution is right, because if you recall, in the linear heat equation, if we integrate the amount of field over the entire domain, the derivative of this would be 0 in the linear one, right? There are some, well, if you use Neumann boundary conditions where you require derivatives to vanish at the extremes, right? But here, because of this nonlinear term, we actually have this instead, okay? You see that the variation of the field is actually the integral of the square of the gradient on x, and then since this term is always positive, right? If b is positive, this derivative is negative, which means that the total amount of field decays. And if b is negative, this thing here is positive, which means that the total amount of field increases. So you can actually, if you actually solve this equation and you compare with the linear one, when b is positive, you expect to have less field in the simulation than in the linear one. And if b is negative, you expect to have more. So this one, while being very simple, it uses a term which is very typical for a real case, and it's also very simple to validate your solution because, well, it's very simple nonlinearity. Well, without further ado, so let's go. So how do we do this, right? So how do we even can compute this evolution? Well, we do something completely similar to the Crank-Nicholson method. So if you recall, we could write an explicit method, and then, so if we discretize this with the, you see that the second derivative would be approximated by this central difference that we're already familiar with, and then we discretize the gradient del u del x, we would use also central difference. If you remember, discretizing the derivative with the right guy minus the left divided 2 times the step, it is a bit more accurate than the Euler discretization, right? It is second order instead of only first order in the error. And then we could do an explicit method, and then we write the field at time step n plus 1 in function of the field at time step n, and then we evaluate this. The problem, as we have already mentioned, is that this is unstable for very large time steps, and then the solution that we adopted was to go to an implicit method. We use this to define a matrix equation that we later solve. But the thing is, because of this nonlinearity here now, this implicit equation that we have in general will not be a matrix equation. It will be a nonlinear equation that we have no way of, no algebraic way of finding the answer. And then the solution is, well, pretty typical if you have seen numerical methods in the past. There is the so-called Newton method. Some books call it the Newton-Raphson method, where you simply get an initial guess, and based on the derivative of this relation, you can improve your guess, and you usually can improve your guess very, very fast, something like 5 iterations, or even less than that. You can already get something which is pretty accurate. And then this is what these notes actually aim to do. They will introduce some notation so that you can write this implicit nonlinear equation, and then we will write down exactly the iterations that we need to do to converge to it, right? So if we have this, now we have a function f at space point I time step n of u equals d, ui minus 1n minus 2uin plus ui plus 1n divided by delta x squared minus b un I plus 1 minus un I minus 1 squares divided by 4 delta x squared. So if we do something similar to the Crank-Nicolson method, we would have the Euler derivative in time, and it will be equal to an average of implicit and explicit time. So we have ui n plus 1 minus ui n divided by delta t equals f, evaluate the time step n plus 1 plus f evaluated at time step n divided by 2, right? Cool. And then, so if we rearrange, we would have ui n plus 1 minus delta t divided by 2 fi n plus 1 u equals ui n plus delta t divided by 2 fi n of u. And then the idea here is that the variables at the time step n are known, and the variables at the time step n plus 1 are unknown. All right? And then here, just to clean up the notation, the text actually calls the variables at n plus 1 u and the variables at n v. So just to make this distinction clear, so we have now ui minus delta t divided by 2 fi u equals vi plus delta t divided by 2 fi v. And now we define the function g iu, which is simply this side minus this one, rearranged a little bit. And then the idea is that when we have the solution that we want, this g will vanish. So the reason that we do this, if we go back to our board, so what is the idea behind the Newton method is that we can write our implicit equation in terms of a function which we want to find the root, right? So we would have something like this. And then we would have, for example, this, right? And this is g. And this is the solution that we want to find. So what the Newton method tells us to do is, well, we would pick a point if we have a gas x0, and then you would trace the derivative here. And then we would find the point here, x1, based on this derivative, and then the idea is that x1 would be a better approximation for the root than x0. Okay, so, and then you can of course repeat this process. You could like pick the value here, and then you would again do something like this, and then you would find x2, and then you would keep going. And the hope is that you would eventually converge to the real root this. So, but first to do all of this, we need this function g, whose root who vanishes when we have the solution that we want. And this is exactly what is done here. We have this function g iu equals this, but notice that if our signal has large n points, here we have one equation for each of these points. We have g1, g2 up to gn, and each of these g's takes u1, u2 to un. So this function g is the function of a vector from our n to our n. And notice that these vectors are different from the vectors that we considered from the 2D case, right? Because the vectors in the 2D case, they were two-dimensional. These are n-dimensional. So this here we are treating our field as the points in our field as a vector, and not really the coordinates where the fields are defined, right? So what we want is when g1 equals 0, g2 equals 0, all the way up to gn equals 0. And then we can write this shorthand saying that g of vector u equals the vector 0. Alright? So how do we do this? Well, if you recall, there is a way to expand up a function for first order. Is a Taylor series up to first order. We say that gi of a vector u is approximately gi at a vector u0 plus the gradient of gi to u0 is scalar product of u minus u0. Alright? And further, if we actually replace this scalar with a vector, all of this is true, yet we have gu approximately gu0 plus jg of u0, scalar product of u minus u0, and this jg, it's what we call the Jacobian, right? It is an n times n matrix whose component is simply the derivative of the ith g function with respect to the j field point, right? So you can see that this here makes sense. Here we have like this is like an n times 1 matrix, and then here we have an n times n matrix multiplied by an n times 1 vector. So when you multiply this is an n times 1 vector, so it all makes sense. So the Newton method arises if we take this as to be exact and force the left hand side to be 0. So we write 0 equals g uk plus the Jacobian of g uk is scalar uk plus 1 minus uk. And if we rearrange, we have that uk plus 1 equals uk minus the inverse Jacobian scalar with g of uk. Alright? And one very interesting exercise is to see how does the linear formalism arise. How, if we actually ran the Newton methods for the linear heat equation, what would happen? Well, very interesting. It turns out that if the functions g are all linear, then this relation here is exact. Alright? You do not have approximately equal, you have exactly equal. So what happens is that for any initial guess that you make, the next iteration of the Newton method would be the root. And another way to see this, if we go back to Krita, so we have the same thing as before, right? So we want to find with the Newton method the root of a function, but now this function is linear, so we have just a line, right? And then what happens is that for any point that you take, if you do the Newton method, take the derivative, would actually go along the line, find this guy here, and that's the root, right? So you can understand the linear heat equation as a very simple case of the Newton method, where you are guaranteed to find the solution after only one iteration. Very interesting. Well, but anyway, so you see here that we have an initial guess, and then this thing here, the inverse of a matrix scalar product with g, this is actually solving a linear system of equations that we're already familiar with. And then we're going to see that this system turns out to be tridiagonal. So without further ado, let's go to the next part, which is actually to compute the Jacobian. And to compute the Jacobian, we have the following identity, is that the partial derivative of the ui component with respect to the uj component equals the Kronecker delta of ij. This is 1 if the integers are the same, and 0 if they are different, right? Which makes sense, because if you, for example, have a formula that u1 appears, if you derive with respect to u1, it will be 1. If you derive with respect to u2, it will be 0 because u2 is a different variable than u1, right? And then just to clean up the notation, we introduce these alphas as before, alpha d. We have one alpha for each term. We have alpha d equals d delta t divided by delta x squared, and alpha b equals b delta t delta x squared. And then here we see that the partial derivative of gi with respect to uj is the Kronecker delta minus alpha d divided by 2, and then here we see delta I minus 1j minus 2 delta ij plus delta I plus 1j plus alpha b divided by 4 ui minus 1 minus ui plus 1 delta I minus 1j minus delta I plus 1j. So here you see like this property that the only terms where this is not 0 is when j equals to I minus 1, I or I plus 1, and this is essentially the definition of a three-diagonal matrix. So we see here that the Jacobian is a three-diagonal matrix, and so that we can evaluate this problem by solving a linear system very, very efficiently. So what would be our loop to compute the Newton method? Well, it would be simple. We will have the configuration of the field at a given time, and then we need an initial guess. And for this guess, we could use, for example, if we want to evaluate the field at the time step n plus 1, we use as initial guess the field at the time step n. Then we evaluate g, and then you notice here that this g depends on the field, right? So this g, of course, depends on the field. There's the u appearing here, right? And the Jacobian also depends on the field, because you see because of this, if it were completely linear it would not depend, but this non-linearity is called it to depend on the field. So every step of the loop we evaluate g, then we evaluate the Jacobian, then we solve the linear system, and then we update our iteration. And the idea is that after some amount of iterations, we would be very, very close to the real solution. So if you recall what we did in the Crank-Nicolson method, what was the main loop? We did a convolution, right? And then we solved the linear system. And the matrix that appeared in that linear system was the same for all times, only the independent coefficients changed. But here it is different. Instead of a convolution, we evaluate this g, which is a more general thing. And then we solve a linear system, but now we must compute this matrix on the fly. And then we update u and do it again until we converge, right? So if we go now to the code, all right, so this is my code for, it is the signal that we are already familiar with. And it has all the stuff to set up the problem, and in the beginning here we have the solution using FFT, but now we are using Neumann boundary conditions. If you recall, in the previous videos we used the Dirichlet boundary conditions. So here, because that the amount of field is a good way to see if we got the problem right, we have changed to Neumann boundary conditions. So, and then here we have what from line 47 we have what this class really is about. We have set up the Newton method, and then we have m equals 30. We divide the time step 30 times, and then, well, we have n, it is 100, it is up there somewhere, and then we have dx, and then alpha d, and then we set alpha b directly here, it is set to 5. But so how does this code work? First we have to compute f, because if you go back to our notes, we have, so to compute g, we need to compute f for u and f for v, right? And then this is exactly what that compute f function does. It is, well, actually we adopt the convention in the code that is delta t is inside the f. Not really that's important, because when we put this delta t inside, we have all these alpha d and alpha b constants appear in F, but it's just a small detail, right? And then we have, where is it? Here. Then we have compute G, which is exactly the formula. It's U minus V minus 0.5 f of U plus f of V. It's just exactly this, but with delta t inside, right? So, and then now we have the computation of the Jacobian, and then this one is a bit more elaborate. Well, you see that there's the main diagonal, which is 1 plus alpha d. Always, if you substitute in this formula I equals j, you would see that it would be always 1 plus alpha d. And then there is the bottom diagonal and the top diagonal, and then there's these zeros here. It is just a SciPy convention, because SciPy requires the vectors to have all the same size, so you need to pad it with something. And then these terms here, they're done outside the loop there because of boundary conditions. Because if you substitute, for example, j equals I minus 1 at the very first term, because we're using Neumann, these terms ui minus 1 minus ui plus 1, they would be the same in Neumann boundary conditions, so this guy would vanish. And further, we would need to multiply this guy by 2, because this is what you need to do in Neumann boundary conditions. And this is what is done here, just that. And then finally, we fill the diagonals with this stuff. So you see that the difference between the bottom diagonal and the top diagonal is just the sign of the alpha b term. And then once we compute the Jacobian, we have the Newton, which is, see, we get a field configuration V. Then we declare a field U equals to V, and then we run 5 times that the displacement D equals to the solution of the Jacobian of U, and compute G with the nu and V, and the new U equals U minus D. And then here, just to check, I print the sum of squares of the G, and the idea is that this should be very, very close to 0 for our solution to make sense, right? And then once we have all this set up, it is actually very simple. We just run m times y equals the Newton iteration of y, and then we should be done. All right. So if we run this, you see. Okay, so see how it all makes sense, because these are the errors, and this is like 10 to the minus 30. So it's pretty much 0, right? See, with only 5 iterations, we could get very close to 0. This is pretty much in the limit of double precision. Even if we had an exact method, the precision would be like this because of the limitations of the computer. And then you see that if we put alpha b equals 5, so we see that the nonlinear one is below the linear, right? Because we used a positive value for b. If we used instead a negative value, you see that the nonlinear one is above. Now, from the theoretical analysis that we did before, right? And if we used a positive one but not as big, for example 1, you see that it is below, but very little, not as much as in 5. And of course, if we set it to 0, then we're actually solving a linear problem, and then they should match, right? If we put this, you see we have an exact match here. So I will see our formulas make sense. We managed to successfully implement the Newton methods, and that's it for today's video, ending The next one we'll start to assemble all that we learned in the previous ones to actually implement an efficient nonlinear filter that we can apply to an image. But that's it for now. Thanks for watching and goodbye.